Hi all, today we will learn how to exploit a buffer overflow vulnerability. To understand the vulnerability, we will take a look at how program stack works first, and then learn how to overwrite the return address on the stack to change the control flow of a program. Before starting, we have week 1 due date on next Tuesday, so please do not forget to submit your flags to our scoring server. You can have late submissions, but it will give you only the 50% points after the April 15th due date. And after a week from that due date, in other words, after April 20th, you will get 0 points from week 1 challenges. So yeah, please finish week 1 challenges by either of the due dates. And let's start week 2, and then the objective of week 2 is to understand how stack works in x86 and AMD 64 application binary interface, and understand why a buffer overflow could be a security vulnerability, and identify a buffer overflow vulnerability in the program, and exploit the buffer overflow vulnerability to hijack the control flow of the program. Then, let's start with the x86 stack first. As we learned from the previous lecture, the program stack stores a local variable. We can access them by having a negative index over EBP, and it stores a function argument passed from the color. We can access them by applying the positive index over EBP. And the function, and we can pass some of the arguments to the callee using non-negative index over ESP. So please don't forget, do not confuse about the positive index over EBP means like that we are getting function arguments from the color, and applying the non-negative, the 0 or positive index over ESP means that we are passing arguments to the callee. And this is so-called a calling convention. In x86, we pass function arguments to callee using ESP. So as a callee, we need to get the arguments from caller from the stack too. So the value stored at the multiplied by 4 over ESP indicates the nth arguments. For example, 0 ESP, that is the first argument, and we can access it from callee by applying the 0x8 over EBP, and we will see these kind of the ESP and EBP matching in the later part of the lecture, but please note that like the 0 ESP means like the first arguments, 0x4 ESP means the second argument, 0x8 ESP means the third argument passed to the callee. And from callee, we can get its argument from 0x8 ESP as a first argument, 0xC ESP, which is 12, as a second argument, 0x10, 16 as a third argument. And in AMD 64, which is a 64-bit version of the x86 architecture, it has more registers than x86. It actually has 8 more registers than x86. So we pass arguments using registers because doing that is faster. Because if we use stack, it involves memory access. But if we pass the value across the registers, it does not involve memory access, and it's just register passing. So in general, memory access is around like 200 times slower than the register access. So that's why in AMD 64, we pass arguments using the registers. And the order of the argument order of the using the register and the AMD 64 calling convention is that the RDI indicates the first, RSI indicates the second, RDX indicates the third, RCX is the fourth, R8 is the fifth, and R9 is the sixth. So please memorize this order to solve challenges. in week 2 for AMD 64. This order is very important. And then some might curious about like the what if we have more than 6 arguments, and then like even in AMD 64 we will use a stack for having more arguments, passing the arguments more than 6. So 7th argument will be placed on the 0 RSP. Yeah. And then the callee also uses these registers to get the arguments from the caller. And here are the examples of the how argument passing works. With an example of the printf, we have an example in x86 on the left side. You can see how a single line of code, so for example, this printf can be translated into like several lines of the x86 assembly lines. And to pass the first argument, so we can identify the first argument as like a 0 index over ESP, and then like it gets a value of the EAX, and then that comes from LEA 8048727, and for the second argument, it comes from ECX, and then ECX is from like EBP-8, which is a local variable. And then the third argument comes from EDX and passes to the ESP, and then EDX is from the EBP-C, so it conforms to like the printf first argument, this one, second argument, EBP-8, third argument as a EBP-C, And on the right side, you can see that how the same function call, like it has a different address of the first argument, but the same printf function call with the 3 arguments will be translated in the 64-bit architecture of the x86, which is AMD 64. So the first argument is passed over using the RDI register, so we directly put the address of the first argument to RDI, and then second argument the variable RBP-8 to RSI, and then third argument RBP-10 to RDX. So this looks much simple, right? So in AMD 64, because we have 8 more registers, so we can use like these registers for passing arguments, and it's faster because it does not involve any kind of the memory access doing such. And the reason why we have a RBP-8 or RBP-10 while we have our EBP-8 and EBP-C here is that in x86 each block or like each of the integer will be like the 4 bytes. So 8 plus 4 is 12, so that's why it is 8 and C. And in 64-bit we have each integer as 8 bytes. So the first local variable could be at like RBP-8 and the RBP-10, which is like the 8 blocks away, 8-byte blocks away. Then we can put in another integer in 64-bit. And another interesting point, another important point is that the register name starting with E is actually indicates extended AX. Because the Intel architecture developed from like a 16 bits first, so AX register is a 16-bit register, and EAX, extended AX register, is a 32-bit register, and then in AMD 64, the prefix for the 64-bit register is R, so RAX, RBP, RDX, all these things are indicating like a 64-bit one. So the rule of thumb is like if you see the E on the register name as a prefix, then you can regard that as a 4-byte as a 32-bit one. And if you see the prefix as R, then you can regard that as a 8-byte 64-bit one. Then, how stack usage work in AMD 64? So we use the local variables, same as like in x86. We store the local variables on the stack, so you can see that the negative index access over RBP, as a local variable. But for the function arguments, we pass arguments using the registers in this order: RDI, SI, DX, CX, R8, R9. Yeah, so please memorize this order, and then like you can easily identify that this will be the first argument, second argument, and third argument. So to pass the arguments to the callee, we do not use stack and just move the register value directly to the target argument register. And then also the callee will get the arguments from caller using the register. So move RDI to RAX means that we will get the first argument to the RAX, and move RSI to RBX means like that we will move the second argument to the RBX. Now we know the three basic parts of the elements of the stack: local variable marked with the green color, and the argument passed from the caller as marked as a yellow color, and the arguments passed to callee as marked with the purple color. And in addition to those three elements, we have two more elements which are very important in exploiting the buffer overflow vulnerability, the topic of this slide. And they are return address and saved EBP. Yeah. And I marked them as a blue color in the stack as well. And as mentioned in previous lecture, this program stack maintains a frame of a function for all these elements for storing the passed argument, local variables, arguments to pass, and also stores return address and then the saved EBP. Yeah. And it grows downwards. It means that the EBP always points to the stack bottom, and the ESP always points to the stack top. So it grows down. So this is stack top and this is stack bottom. And for next, let's see how such stack grows down when we have a function call. And I will take an example in the our first challenge, BOF level 1. And in the main function of it, it calls a function receive input. And I will take this as an example and show how stack grows using this code. So the initial stack state before calling the function look like this, because we don't have any kind of the local variables in the main function. You can regard that. So there could be some of the values stored in here, but to simplify the problem, simplify the case, we can regard nothing on the stack. Yeah. And then when execution hits call 0x80485670, so which is a call receive input, then the stack will change as shown on the figure. So what it will do is like it will first store the next instruction address to the stack and move ESP one block down. And the reason for doing this is that so the calling receive input means that we will start executing another function, and then when we finish the execution of this function, we want to return to the next instruction of this call instruction to continue the main function. Yeah. And to do that, we need to record where the program should return on the stack. So for that purpose, we use the stack, and the call instruction automatically records that into the stack. And the reason is the call instruction, although it looks like just a one-liner instructions, internally it runs as two lines. These are push EIP and jump to the call target. So what it does is, so the EIP always points to the next instruction to run. So push EIP means that it will put the address of the next instruction to the call to the stack, and the push also shift down the ESP one block down, and then in 32-bit machine, this one block is 4 bytes. So what it does is like put the next instruction address to the return to the stack, and then move the ESP the 4 byte down. So we see that the ESP gets one block down, and then the stack stores the return address here. And after the function call is done, the execution hits to the head of the receive input, push EBP, so it will store EBP on the stack, something like this. And please note that the ESP moves one down because the instruction is push, so it will automatically get the ESP down for 4 bytes, like this. And the reason for doing this is that we will create a new stack frame used for like the receive input, so using EBP. And before doing that, we store the saved EBP. So we store the previous value of the EBP because we need to restore that when we return to the main function, because that EBP will point to the start of the stack of the main function. So this process is something like that we will create a new stack frame for a new function right after calling the receive input function. And then we store the previous EBP value to the stack. And then the next instruction is the move ESP to EBP. So we will set the value of the EBP to the value of the ESP. So we will get down EBP to here. Yeah. But please note that we saved the previous EBP value in this location, so we can restore that. So that's actually the start of the stack of the main function, and then we can restore that when we return from the receive input function. And the instruction will make the EBP down to the ESP, and the EBP now points to the new bottom of the stack. And then the next instruction is the push ESI, and we do this because this function uses ESI to store some value, and at the time of the return we want to restore that the value of the ESI to the original value that the main function expects. So basically these head of the stack are used for storing values from the caller, and later we will use these values to restore all such register value and return to the correct point right next to the call instruction to continue the execution. Yeah. And then the next prologue instruction of the function is a sub ESP for 54, 0x54, and what it does is it actually reserves the stack for local variables and argument passing. So ESP is now here, and subtract 54 will create the several blocks, so we can reserve the stack for the local variables. For the next, let's continue to see how a function call in this receive input function work. So these assembly code snippets are extracted from the receive input function, and it's for calling printf with the 3 arguments. And suppose that there is a function call printf here, and then the first instruction here will put the value 41414141 as a local variable at EBP -8. So the stack diagram would be something like this. And the next instruction is putting the variable 42424242 to 0xC EBP. So the stack diagram will be something like this. And 0xC here is like the hexadecimal number, so it's 12 in decimal. So EBP -4, 8, 12. And after running few more instructions, because it does not change the stack, so I skip that, and we are at the moving EAX to the location pointed by ESP. So This EAX comes from the LEA 0x804877 to EAX. So what we do is we will put this value into the address pointed by ESP. And then the next instruction is putting ECX to ESP plus 4. So ECX comes from EBP minus 8. That's the 41414141. So we put that value to ESP plus 4 here. And then the third argument, EDX. So it comes from 42424242. So we put that value at the ESP plus 8. And this is how we put the arguments for the stack. Yeah. And then the next instruction jumps to the printf. And note that we will, when we call printf, the CPU automatically stores the return address, the address of the next instruction to the stack. So after running this, so the stack composition will be something like this. So ESP will get 1 down, and then it will store the return address, and the return address will be the address of this instruction. So after the printf function returns, after the printf function is executed with these 3 arguments and then returns, it will return to the receive input function, location pointed by here. So this is how the x86 ABI application binary interface supports using the stack to support the nested control flow change. So even if we change the control flow to printf, when it returns, it will return to this address. And basically this kind of the stack frame will be what printf will see. And we have passed the 3 arguments and store the return address, and its function prolog saves the EBP and reserve the stack space, as we have seen the prolog of the receive input, something like this. So this printf will do the same thing with this one, and then use their own stack space. But we will pass this kind of the stack composition to printf, so that printf can access the first, second, and third argument. Then next, let's take a look at how function return works. We will see how the receive input returns to the main function from this stack frame. The following 4 instructions are at the end of the receive input, so we will just follow the execution of them. The first instruction is to add 0x54 to ESP, and this will simply restore the ESP right at the save the ESI location, because we stored the save ESI before running sub ESP for 54. So this 0x54 should be matched with this add 54 to restore the ESP value exactly at the right before to the subtract when we subtract the value. So it will make the ESP up here, and then the next instruction is a pop ESI, and this will restore the value of the ESI we stored previously. So make it to be the value that the main function expects. And this pop instruction will move the ESP 1 block up. So now ESP and EBP points to this same address. And then we run pop EBP. That will restore the value of the EBP to the saved EBP value, which is the EBP of the main function, which indicates the bottom of the stack of the main. And the pop instruction, so there are 2 changes. So EBP will point to the what it should be, so the bottom of the main function's stack, and then ESP will go 1 block up because the instruction is pop. So there are 2 moves, and then we run the ret instruction, the return instruction. The meaning of the return instruction is simply the pop EIP. Although we cannot access the EIP register, you can semantically think it as like a return instruction is equivalent to the pop EIP. So it changes the instruction pointer. So we will pop this return address and put that to the instruction pointer. Then the execution continues at the point pointed by the return address, which is 8048.866b. Yeah. And this is how call return works. So after running the return instruction, we will return back to the somewhere in the main function right next to the call instruction of the retrieve input and continue to execute. Next, we just learned about how stack works, and next, let's learn about what is the buffer overflow vulnerability. The code in the figure shows an example of a buffer overflow vulnerability. This is the same code that we have in BOF level 0 challenge, so please refer to this slide when you solve the level 0. And we have a character buffer, a variable buff, size 20 at here. Yeah. And then somewhere in the bottom, when we get an input from the user using fgets function, we use the maximum size as a 128, which is bigger than the buffer size 20. This is the case of the buffer overflow, and let's take a look at the why is this causes a problem. So having the more size for the input than the size of the buffer, why does that cause the problem? So, and basically, buffer overflow is about like overriding values in stack by overflowing a local variable buffer. Yeah, and that lets us like the overriding some of the values in the stack. That could be local variables or the control data such as a saved EBP or a return address. So to simplify the diagram, so I changed the buffer size. So suppose we have the buffer size 4 at EBP minus 10 right at here. Yeah. On the right side, you can see buffer here, and we have other local variables here, and also we have control data are there. And then suppose you have a fgets function called to the buffer and read up to 128 bytes from your standard input. Then let's see what will happen. So if we put more than 4 bytes, the original size of the buffer. So let's take an example of putting 12 bytes, for example, 1111 A, B as an input to the buffer. So right now we have a 4-byte buffer and we put 12 bytes. So we will do 4 byte by 4 byte. Then it will first put 1111, which is 31, 31, 31, 31 as an ASCII code to the buffer like this. And then next we will put A, which is the 61616161 as an ASCII character to the next block. So you just saw that like we have a buffer right here. First 1111 overrides the buffer put on the buffer. This is legit, but the next 4 character A will unintentionally override the local variable stored in the right next to the buffer. And then the next one B, that will overwrite another local variable to the next. So basically, by overflowing the buffer at here, you can change value of the other local variables. And not just for that, you can also change, save the EBP, save the ESI, and even change the return address. So if you put longer values to the buffer, you can overwrite up to this point and more. Then let's overwrite the return address to see what happens to the program. Please recall that we stored this return address as right next the address of the next instruction to the call of the receive input. Yeah. So that when the receive input returns, then it can return back to the original the points to continue to execute the main function. And we will gonna change that this value using the buffer overflow variability and see how it can be and what will happen. So right now we have a 4-byte buffer, and what if we type like the more longer values, so 1111 A, B, C, D, E, like this. So this is a much longer than like the 12-byte input. Then like this is the state up to like we override the BBBB, and the CCCC will override the save the ESI, and DDDD override the save the EBP, and EE will overwrite the return address. So we can overwrite the return address. Then what's the problem? This return address will be used for returning to the instruction point to execute after finishing up the running the current function. So if we change this, we can change the program's execution. For example, if we change this to the valid address of the another function, for example, the address of the ghetto shell, then the program will execute that. Something like this. And suppose we put the address of the ghetto shell function at here, and let's see what will happen. So this is the function epilogue of the receive input, and it will first add 54 to ESP, and then restore ESP, restore ESP at here, and then pop ESI. So the ESI will have a read value 63, this one, but we will not care. And then pop EBP. So the now EBP register will have an invalid, not an address value like this, but we will also ignore that. And then we will do return. And where it returns to? It returns to the function address, to the ghetto shell, and finally it will run this function instead of the returning to the original point that the main function has. So the main objective of challenges for week 2 are you need to identify the size of the buffer in the program, and then try to overflow the buffer to control either local variables or return address, and then run get a shell function to inherit the privilege and then read the flag. By following the lecture today, you can solve up to level 4, so please work on those challenges, and each line here gives a brief summary of the challenge. And the due date of this assignment, not just for these 5, and then we have a total of 10 challenges. Due date of this assignment on like the April 20th, so it's more than a week from today. But please start earlier to not too late for the flex submissions. Thank you, and the videos will be followed by this lecture.